Today we have, well, this is part 2 of Ygal Fest. So today we have Ygal Klein giving us our astrophysics seminar. Ygal is a newish member here who's been here since November. After receiving his PhD, he did alongside, advised by Boaz Katz, a former member here too, at Weizmann Institute. In the few months that Ygal has been here, we've had plenty of productive arguments about dynamics, and Ygal likes to delve very deep insights into very classic problems, and there's no more classic problem than few body dynamics and simple pendula. So this morning he already told us about how the Lidov-Kozai problem maps to a simple pendulum, and we're going to have some more along those lines now, and so take it away, Ygal.
Thank you, Chris. Thank you everyone for coming. Today I'm going to talk to you about the seemingly contrast between the complex high-E dynamics of three-body problem and what is called the simple pendulum. Might not be so simple. Actually, when somebody mentioned, and it is true that when I was here like 2 years ago, I gave like a 15-minute short talk about some of these results, but I think in this 1-hour seminar, we can go more into it. So this work, as Chris mentioned, was done with Boaz Katz during my PhD. Just a quick overview of things that I did on my PhD. I did both analysis of observations of multiplicity of A stars, and also theory of dynamics, few body systems dynamics. They have deep connections of astrophysical applications that you're all invited to talk to me afterwards. I'm going to be the subject of the seminar. Okay, so basically, I would like to achieve in this seminar to explain to you different dynamical problems, which we can simulate numerically. And we have also managed to solve them analytically using a simple pendulum model. And all these 3 problems are like general plots of comparisons of numerical simulations dependent on initial conditions. So the axis and Y in 3 plots are initial conditions of some problems. And you have numerical simulations and analytical predictions which follow them. And all of these models are simple pendulum models. And we're going to tackle them one by one, whatever we achieve in the time that permits us. Okay, so the we are talking about the 3-body system. And we are going to make a lot of approximations about it. So we have 3 masses, M1, M2, and what we're going to call M pair. We're going to assume that M2 is a test particle, so its mass is negligible compared to M1 and M pair. This is one approximation. This means that just that M pair is Keplerian moving on a Keplerian constant orbit around M1 because M2 is not perturbing it. And we're also going to assume that this system is hierarchical. So M1 and M2, M2 is revolving around M1 on a Keplerian orbit. And the orbit of M pair is much farther away, so it slowly towards the orbit of M2 over. These are the assumptions that we're going to make from the general 3-body problem, which has a lot of astrophysical applications. Of course, astrophysically, these are the systems that we see, because as they take the hierarchy down, not in mass, but in separations, at some point it becomes unstable. So if systems are stable, we don't see them. So astrophysically, basically, these are the high multiplicity systems that we see. Hierarchical triple systems. Okay. These systems have a lot of applications in astrophysics because there is a striking observational fact that about 1% of stellar objects have some companion, either it be planetary or stellar, which is very, very close to it, orbiting on this orbit. And the formation channels of these systems, this could be hot Jupiters, warm Jupiters. Well, gravitational waves are coming from black holes. They merge in Hubble time, so they must be very, very close at the point that they are black holes. You have merging stars, merging white dwarfs, producing type 1 supernova. So astrophysics or energy astrophysics demands a close companion of some sort. And indeed, as I said, 1% of stellar objects have this close companion. The formation channels of the system is still an open debate, and it might be different formation channels from different scenarios. But one formation channel is intrigued by what has been found numerically using n-body and also average equations, that extremely high eccentricity can emerge, or at least start in numerical simulations of this hierarchical three-body system. So starting from 2000 and many papers since then, there have been numerical solutions of the three-body problem on the left side, and also four-body problems. And people were following the eccentricity of the inner orbit. In the hierarchical system, you have an inner orbit, and the eccentricity can get exceedingly close to 1. So this intriguing numerical observation led to the construction of formation channels of the different astrophysical scenarios. We want to understand how these eccentricities emerge. In order to set the language straight, so as we said, we have a hierarchical three-body problem. M1 and M2 revolve around each other in what we are going to call the inner Keplerian orbit. And since M2 is a test particle, the perturber is moving on a constant ellipse, a constant Keplerian orbit, which is going to define for us the coordinate system. So the z-axis is going to be aligned with the total angular momentum, which is the angular momentum of the outer orbit, since the inner orbit angular momentum is negligible. And we are going to align the x-axis on the eccentricity vector of the outer orbit. So the outer orbit is some ellipse, has an eccentricity vector, and it's constant, so we are going to put the x-axis on that plane. It's a Keplerian orbit, so there's a connection between the vector j and the vector e of the outer orbit, and its eccentricity through these connections. Now we're going to define some what we call orbital elements. So we have a plane, the xy plane, which is the plane of the orbit of the outer perturber, which is constant. We have the orbit of the test particle around M1, which changes with time. And it's also a Keplerian orbit due to the hierarchy of the system. But it has a plane of itself, which is not the xy plane. So there is some angle between these two planes. We're going to call this angle inclination, which we're going to name it I. And we have the component of the angular momentum of the inner orbit. We have its component on the z-axis, which is just the square root of my minus c squared, cosine I construction. So we have an inner orbit with its own angular momentum. And we have some angle big omega, or large omega, which is defined here as the angle between the x-axis of our coordinate system to the vector z cross j. Now, in the plane, inside the plane of the Keplerian, of the inner orbit, the orbit can precess, so it has an angle between some x-axis in its plane and the pericenter. We're going to call this angle small omega, and the connection to the components of the eccentricity vector is Ez is E sine I sine omega. Okay. Let's try to track this system numerically. We take a three-body system. As I said, this is many parameters. So stating the problem depends on many parameters. We have the masses. We have the parameters of the inner orbit with semi-major axis and eccentricity. We have the parameters of the outer orbit with semi-major axis and eccentricity. And we have all of these angles of orientations. So this is a many parameters problem. We can take some n-body solver that you like, whatever you want, you can write it yourself or give us something from the shelf, and solve the time evolution of the different parameters of the orbits. Now, as one can see, this is a real n-body simulation using these parameters. As you can see, the hierarchy of the system justifies an approximation, but there is no energy change between the orbits. And indeed, the semi-major axis of the inner orbit is constant, basically constant. What comparing to the constancy of A, there is a striking change in the eccentricity of the inner orbit and the inclination of the inner orbit. This is long been known, developed by Kozai-Lidov, solved analytically in the 60s, and since then we've been studied a lot. But as you can see, 1 minus E is in log space, so E can change from 0.2 to 0.9, which is significant. These oscillations are called Kozai-Lidov oscillations. But it turns out one variable of the components stays constant. This Jz, as I said, it's the projection of the angular momentum of the inner orbit on the z-axis. Numerically, for moment on-body simulations, it can be from -1 to 1. You can see it's constant. So there is some constant which connects the eccentricity and the inclination. They must preserve this constant, so the oscillations are coupled. And it changes significantly, the pericenter changes significantly, and this leads to all of these dynamical channels when you start from some general orbit of some separation, circular orbit of a planet, whatever. But if its pericenter can go down to a very close proximity, other physics can go in, like tides, that can take energy away, or gravitational waves, whatever, and the orbit can change. So this is like the first step to explain information, dynamic information channels of different scenarios. Okay. This n-body simulation that I've just shown you can be approximated analytically by taking the Hamiltonian of the perturber, expanding it in the small variable of the ratio of distances between the two inner particles and the farther one. This is a small parameter. The Keplerian potential can be expanded in small parameter. And the leading order is a quadrupole, the quadrupole order. Now, the time scale of these oscillations of E and I is much, much longer than the periods of the two orbits. So we can average both orbits, which is the approximation that is called quadrupole double averaging of the Hamiltonian, and we get this structure of Hamiltonian. So now what we are tracking is the components of J and E of the inner orbit. Of course, the outer orbit is constant, and these components change with time according to the Hamiltonian, which depends on them, of course. Now, JC is constant because it turns out at this level of approximation, the potential is axisymmetric. So JZ is constant. The potential itself is, of course, also constant. So we get another constant, which I will call CK from here on. And it's just E squared minus 5/2 EZ squared. It's a term inside the Hamiltonian, which turns out to be constant since phi is constant, or h quad is constant, and JZ is constant since h quad itself is axisymmetric. Okay. Indeed, we go back to our n-body simulation and we plot this CK. It's quite constant. So it can change from minus 1.5 to 1 generally, but it is constant. In the level that JZ is constant, but E and I oscillate. Okay, so it looks like at this time of the simulation, the double averaging quadrupole approximation reconstructs the oscillation. So we take the averaged equations from this quadrupole Hamiltonian, we plot them on the n-body simulations, and the approximation is justified. It reconstructs the n-body result. But we wanted high eccentricity. The astrophysical motivation, or we looked at the numerical simulations that others did, and extremely high eccentricity emerged. But if we have a constant JZ, we have a variant on E, because E squared plus J squared is 1, and if JZ has some component which is stuck, E max is stuck. So we have some barrier on E, and it's not good astrophysically because it's not enough to get close. Basically, you can JZ is constant. It comes from initial conditions. As JZ is low, E can get high. As long as JZ is higher, or the absolute value of JZ is higher, the barrier on E is more strict. But taking the numerical simulations to longer timescales, we see that extremely high eccentricity does emerge in this setting of parameters. So what looked like as a constant JZ at short timescales, you can see a long-term deviation of JZ compared to the secular approximation of constant A. So A stays constant in the n-body simulation, what stays constant in the approximation. But what we thought that JZ is constant, there is a long-term deviation of JZ from its starting value. And we can see that when JZ crosses 0, it coincides with this extremely high eccentricities in the simulation, and also a flip of the orbit. So I crosses 90 degrees, and the orbit flips orientation. So n-body, taking it to longer timescales, shows a change in JZ, extremely high eccentricities, and a flip. The quadrupole approximation cannot reconstruct it, of course, and indeed it doesn't. What gives us a good approximation is taking the expansion of the potential to the next order, octupole order. So now we have a different Hamiltonian, which is composed of the quadrupole Hamiltonian plus a small perturbation, depending on this ratio of 7 major axes and the eccentricity of the outer orbit. As you can see, this perturbation goes away if the outer orbit is circular, and it also gets weaker or takes more time if the system becomes more and more hierarchical. But although this being a small perturbation on the quadrupole potential, since quadrupole potential told us that there is a constant, then even a small perturbation can break its constancy and take it in through a much longer time to cross zero and take the eccentricity to exceeding it close to 1. So now we are going to track the average. We're still double averaging the orbits, but the Hamiltonian we're double averaging as the next order, the octupole order, which does depend on JZ and can let JZ change. We put the averaged equations solution on the n-body, and it reconstructs the deviation of JZ, it reconstructs the eccentricity and the flips, of course. As you can see, we now have another term in the definition of the system, which is the strength of the octupole. It will be very low, depends what's low, but this is a low value. But as I said, since JZ was constant in the quadrupole approximation, even a small perturbation can change can make it deviate from its starting value to 0 and let you get to high eccentricity.
Is there some other concept quantity, even with the octupole?
No. So you had CK in the quadrupole. Okay. That was because the quadrupole Hamiltonian was constant and JZ was constant. So you had CK. Now both of them are broken, and you don't have only H oct. Only the Hamiltonian octupole order is constant at octupole order. Okay. This is the only constant.
Okay.
Does the black line here assume that the octupole order is much weaker than the quadrupole?
Yes. So H oct is the total Hamiltonian at octupole order. It composes of the quadrupole Hamiltonian plus this parameters dependent prefactor.
So you need some phi oct. You solved linear order in epsilon oct.
Yeah, this is linear order in epsilon oct, and this small parameter, taking this parameter to be large can be due to two things: making the hierarchy small or making hyper large, right? This will break stability at some point. So epsilon oct has a barrier just from stability considerations. Now, this is like epsilon oct of 0.1, but this is another talk. Being it lower than 0.1, make the system stable, but let's JZ slowly deviate. Okay?
What sort of physical system should I have in mind here? Because these octupole things take a long time to act. The longer you wait, the more likely it is that something else happens to the system, fly by or something like that. So what's the perfect case? Like an isolated triple star? Or?
So an isolated triple star, first of all, an isolated binary with a planet. This is like what is called S-type, but hierarchical S-type. So there is the circular approximation, there is no exchange of energy. The perturber is very far from relative to the planet, and it's isolated. And you have octupole if the perturber is moving on an eccentric orbit. You have octupole. Okay. But it's a good question about, we'll get to it at the end of the lecture. Or
even that, there's going to be flybys and things.
Yeah.
But there are systems where this is isolated enough that this is the dominant effect.
Yes.
And I have another question.
Yes.
Did you have somewhere written the say some analytical formula for all the time scales? Because there are many time scales here. For example, how does the Lidov-Kozai oscillation time scale compare with the octupole induced change in JZ?
Okay, so it's not in the presentation explicitly, but so the period of the inner orbit is analytically known. The period of the outer orbit is analytically known. The period of the Kozai-Lidov oscillations at quadrupole order is analytically known. Okay, and they are, if the system is hierarchical, the times or the scaling of the Kozai-Lidov oscillation scales as the period of the outer orbit squared over the period of the inner orbit. This is the scaling, it's not exact, it's scaling. The octupole time scale goes as the quadrupole time scale over the square root of epsilon oct. But this is it's not my result. It's not written here, but these are the scalings.
So it's only controlled by the epsilon oct.
Yeah. As long as the epsilon oct is low, it's only controlled by epsilon oct. Yes. With the caveat that we'll get to. Okay. Okay. So as I said, the three-body problem in general, but even at this simplest case of test particle and hierarchy, as I said, depends on a lot of parameters, the semi-major axes, masses, eccentricities, and angles. And the question of is JZ crossing zero? So we said that JZ sets a barrier on the maximum eccentricity that I can attain. JZ crossing 0 means that the eccentricity is not bounded. So we are going to be interested in the question. We are going to exchange the question of can I get high eccentricity or can I get a flip with a simple question, can JZ cross 0 or not? Because if it cannot, there is some barrier. Now, we can see that this binary question of yes or no, JZ can cross 0 is extremely sensitive to initial conditions. So as you can see, since we took an body in the simulation, we show all of the initial conditions, masses, A's, E's, whatever, angles. And in this case, JZ does cross 0 at some time. But we take the initial conditions to slightly change them. Okay, so for example, the initial eccentricity of the inner binary in this system was 0.2. JZ crossed 0 and there is high eccentricity. Take it to 0.3, nothing happens. So in these plots, again, blue is n body and black is this octupole double averaging. So it reconstructs all of this sensitivity. And this question of crossing 0 or not is very sensitive to initial conditions. Okay? So, of course, taking I away from 90 degrees gives the 0 crossing, which is not surprising. But other variables, so you take omega from 0 to pi half, nothing happens. You take x to 0.3, nothing happens. So something must be hidden in this mystery. Okay. Actually, this was kind of a lie, since there is one parameter that I didn't change in the previous slide, which is the mass of the perturber. So in the initial condition before, the mass of the perturber was 0.1 or 10th of the mass of the host star. But if I take this mass higher, at some point, this binary answer, if JZ will cross 0 or not, fails. So the octupole double averaging approximation fails to reconstruct the n-body simulations. The approximation tells us that JZ will cross 0, but n-body says it won't. So there is one parameter where octupole plus double averaging does fail. And we're going to talk about it. What actually happens when the perturber becomes massive, there are short-term oscillations which are much shorter, but they accumulate. As you can see, JZ oscillates on short time scales. And these short time scales oscillations are not captured by the octupole plus double averaging. But as the mass of the perturber goes down, these oscillations are low, and this approximation holds. Now, this can be fixed. One does not have to leave the double averaging approximation. This can be fixed, and it has been fixed by different authors. And the last one was Scott, compiling the different ways to do it, and then suggesting a way which is very helpful for us, an axisymmetric double average potential. But correcting the double average potential with an added term, which turns out to be axisymmetric, and introducing another small perturbative factor which depends on these parameters, corrects the deviation of the regular octupole plus double averaging from the n-body. And as one can see, when taking this double average corrected Hamiltonian, I'm not sure if it can be seen on the screen, but there is like a CN line here following the oscillations of JZ that emerged in the n-body simulations. This has been compared to n-body maps or flips, and it reconstructs it very, very well. This is not done by myself. It has been done. Okay. What is striking in this massive perturber n-body and corrected Hamiltonian is that it turns out there's some asymmetry in JZ. So if we take the inclination away from 90 degrees, we're making JZ higher. So it's going to be harder to let it cross 0. But the previous Hamiltonian was symmetric around 90 degrees. So it didn't matter to what direction we started away from 90 degrees. But this corrected Hamiltonian, which resolves the n-body results, it looks like 0 crossing of JZ depends on what direction you went from JZ equals 0. So taking the inclination to 60 degrees, which is 30 degrees away from 90 degrees, there is 0 crossing. But taking it 20 degrees higher than 90 degrees, turns out there is no 0 crossing. So this massive perturber introduces some asymmetry in JZ, which is not intuitive. Okay. Now, let's try to analytically understand what I just, in this long introduction of problems and how they are solved, how they are approximated. So we have these Kozai-Lidov oscillations. And so we have oscillations of the eccentricity and the inclination with Jz being equal and Ck being equal. And every Kozai-Lidov cycle is determined basically by 4 parameters. 2 constants, Ck and Jz. The orientation of the orbit with respect to the coordinate system, to the orientation of the perturber. And at some initial time, we have a phase of the oscillations. Of course, it depends on the phase. Now, when we added the octupole, we broke the constancy, and we are going to focus on the regime which allows high eccentricity, so very, very low Jz close to 0. And we're going to focus on positive Ck. If somebody wants to ask me why, later I will tell. So positive Ck with low Jz. But there are no longer constants. So we are going to, the orientation of the orbit with respect to the outer orbit is going to be parameterized by some angle, the angle with respect to the x-axis in the xy plane. So our eccentricity vector projected on the xy plane is some angle omega e, and the Jz equals 0, there is no precession. So the time dependence of this angle is some function of Ck and the phase times Jz. Indeed, this omega e is a slow variable, just like Jz. This is seen numerically, and since its omega dot is dependent on Jz, of course, it's a small variable. But it is a slow variable. Okay. Why is Jz changing when the octupole is introduced? There is, in the quadrupole order, it's a kind of a coincidence, but the potential is axisymmetric, even though the perturber is eccentric. So it exerts no torque on the z-axis, and Jz stays constant. Now, when the octupole is introduced, there is torque, and the strength of this torque is dependent on the length of the arm that the perturber is affecting the inner orbit. And this dependence is a sign of omega e dependence. So Jz dot has this small prefactor, it's the time derivative is very slow by this epsilon oct, some function of the Kozai-Lidov cycle of Ck, Jz, phi, whatever, and the dependence on omega e is sine omega e. This is going to be important. Okay, so we have 2 equations of motions of slowly varying variables, Jz and omega e, which are dependent one on the other by these 2 equations of motion. Omega e dot is some function of Ck times Jz, and Jz dot some function of Ck times sine omega e. These functions can be analytically solved. They have been analytically solved in the past through some methods, and they can be easily analytically solved now using what we talked in the dynamics meeting, but this is another. Okay, just to set things straight, I want to make sure that everybody, that when I say pendulum, you also think about the same thing. So a simple pendulum is some mass with no size that is on a rod, length L, has some angle theta from an axis, and there is some gravitational field. And the force on this mass gives equations of motion of this angle theta. So it has some velocity, theta dot is v, and v dot is some minus some positive constant, sine theta. This system, this mechanical system, has 2 different regimes of dynamics. One, which I will call libration. So theta cannot cross the highest point. It's not just a small angular approximation of pendulum, which is a point oscillator. The angle in libration can be large, as one can see in the right side of the plot. But this should have been a movie. It should have librated. It didn't rotate. It didn't go to the highest point. The other regime of motion is rotation. So the mass can just rotate, never stops. What separates these 2 regimes is, of course, energy considerations. So the initial velocity and the initial height determine if the mass can get to the highest point or not. Another strict separation between these 2 regimes is if the velocity crosses 0 or not. So in libration, the mass stops at some time and changes the direction, so the velocity crosses 0. And in rotation, the velocity doesn't cross zero. Of course, it can be positive or negative depending on the direction of motion, but it doesn't cross zero. So this is another separation between the two regimes. Of course, they're separate. So this is what I mean by simple pendulum. And whenever I see two functions which have equations of motions correlated or dependent or correlated in this way, I call it a pendulum. Now, remember that h oct, of course, was constant, and epsilon oct is small. So phi quad is kind of constant, at least up to epsilon oct, right? And in that case, one does not need to follow the change in ck, because phi quad can be approximated to be constant. If ck is its time evolution is not important, these complicated functions f omega and fj, which are dependent on ck, basically, they have a value at ck is 0, and one does not have to follow their evolution. What we got are equations of motions of a simple pendulum between omega e and jz. So omega e dot is some constant times jz. So the velocity of this pendulum is jz. And jz dot, the acceleration, is some constant times sine omega e. So the octupole effect, long-term effect of the octupole double averaged equations on jz is a simple pendulum model. These equations were written before, but this identification that ck does not need to be followed, and that this can be solved analytically simply by a simple pendulum model is what is shown here.
Wasn't that done by Sidorenko?
Yeah, so Sidorenko was the 2018 mentioned that the octupole can be viewed as a simple pendulum in some sense of the similarity of phase naps, as you said, but this statement algebraically or analytically was not presented. Okay, this is not important. Now, I mentioned that in this pendulum, jz is the velocity of the pendulum. So omega e dot was some constant times jz. We said that the separation between libration and rotation in a pendulum is defined by the question, can the velocity cross zero or not, right? So if jz is the velocity of some pendulum, and its crossing zero is the question that we were trying to track, the question of can initial conditions lead to a flip or not is equivalent to the question, is the pendulum in libration or not, right? And in this plot, what is shown is the following. So the x-axis is ck0, it's the ck of the initial conditions, and the y-axis is the initial jz. We take the other orbital elements, we just scan all possible values of omega, and we mark a point in the ck0, jz0 plane as red if there was some omega, which there was a flip, and if as blue if there was some omega without a flip.
You mean from n body?
No, so this is already octupole double average, but for this kind of parameters, octupole double average was so octupole double average reconstructs n-body results. Now, taking the simple pendulum model, we can put analytical prediction where the boundary between these regions will be, and these are the black lines that you see on this plot, which follow the numerical boundary quite remarkably. In the left plot, there is an equivalent show up of this result. So we start from jz equals 0, and we measure to what maximal or minimal value jz got in the simulation. So now we have different initial conditions. So these are different scatter points on the plot. At some ck0 and j0 equals 0. And every point in this plot, we have a prediction from the analytical pendulum, all of different pendulums, what will be the maximal velocity when we started from 0 velocity. Oh, this is analytically now, and all the points sit very nicely in the simulations. So octupole plus double averaging, when it reconstructs an body at high eccentricity, also at low jz, is a simple pendulum. Now, remember that when the perturber mass grew, there was a deviation between octupole plus double averaging and n-body, and we needed corrections to the Hamiltonian. If we use one version of these corrections, one of Scott's versions. This is an axisymmetric version of the correction, which means that the additional Hamiltonian for the perturber, for the massive perturber case, doesn't change the equation of motion of Jz, since it exerts no torque, no z torque. So the Jz equation of motion doesn't change. What is changing, what is the prominent change of this additional Hamiltonian, is an additional precession of omega e dot. So before we had omega e dot is f omega Jz. Now we have this epsilon sa dependent Hamiltonian, which adds an additional precession. What the massive perturber does is it makes it hard to process omega e. We said that Jz dot and omega e were coupled in the simple pendulum equations before the correction. Adding this correction makes it hard to change omega e. And indeed, comparing low mass to high mass at short times, one can see that this is the blue is the n-body simulation, cyan is the corrected Hamiltonian, which follows it, and black is the octupole plus double averaging, and the precession is larger when you neglect this correction, when epsilon sa is high. Doing the same trick, we can get rid of the CK dependence by averaging over this corrected additional term, and we get another term in the omega e dot equation. But this is a constant term, and it is not analytically from initial conditions. Since we treat CK as constant, and we average over an orbit with Jz equals 0, this function is not analytically. And the equations of motions that we get for this case turn out to be also equations of motion of a simple pendulum. This can be seen by remembering that basically the simple pendulum equations is double dot of theta is proportional to sine theta. And double dot of omega e stays proportional to sine theta since this delta that we introduced is constant. So in the massive perturber case, we also have a simple pendulum model that can be predicted from initial conditions. Okay. We look at a similar plot. We take different initial conditions, all start from Jz equals 0. Now Jz is not the velocity of the pendulum, but it is still a simple pendulum. So it is still separates to libration and rotation of the pendulum. And from initial conditions, we can tell what regime of motion the pendulum has. Does it have libration? Does it have rotation? And from Jz equals 0, we know from the simple pendulum model a prediction of the maximum or minimum value of Jz. We take different initial conditions and we measure to what value Jz max or min got in the simulation. So first of all, numerically, we can see the break in the symmetry between negative and positive Jz, since there is this high island in positive Jz. There is no such island in the negative Jz. And we see the different regimes of libration and rotation of the pendulum separating. There's like places where Jz cannot get, right? Because of this separateness between libration and rotation of the pendulum, and each initial condition is predicted from the simple pendulum model, and it reconstructs quite significantly. The black curves in this plot are the curves without the correction. So these are the curves for the previous just octupole plot. And what the correction is doing is creating these islands, both in the left side and the right side, and breaking the limits of this black curve.
With the blue dots rotation.
So there are shaded colors in this plot and there are dots. So in this plot, there are black X's, okay? Black X's are numerical simulations of double averaged equations of this corrected potential, starting from Jz equals 0, different omega e's, these are the scatter points, and different CK0. You start from Jz equals 0 and you measure Jz min and Jz max, okay? And you put a black cross. Now, each initial condition has a simple pendulum model, so you can predict analytically Jz max and Jz min, okay? And these are the red circles on scatter of the process, and they coincide. Now, the shaded regions are taking this plane, we can tell at what locations in the plane there is going to be some result, because the pendulum can exist there, and what is the dynamics of the pendulum there. These are the two colors. So like a blue shaded region, there is a pendulum there and it's rotating. A red region in the plane, there is a pendulum there and it's liberating.
But the blue also lies inside the Lagrangian zone, no?
Where?
What? So which one is the Lagrangian?
So
one is
this is liberating pendulums. These are rotating pendulums. This is liberating pendulums, rotating, liberating, rotating. There's no mixture between the colors of the regions, of course. Although, put aside what I said in the morning. A pendulum does only rotate or librate.
Then what does this curve mean?
So
Black curves.
So the black curves were without the correction. We had this plot, okay?
Yeah.
So double averaging plus octupole without the correction, which are correct with a low mass perturber. We have these black curves, which in this analytic picture is the boundary between libration and rotation of the pendulum.
So the red is librating, blue is rotating in this case.
No, in this, yes and no. So here, red and blue are actually marking of the numerical results. So you have a point here. You start from JZ 0 of some value, CK 0 of some value. You take omega E 10 values between 0 and 360 degrees, okay? And if one omega E had a flip, I mark this point as red, okay? Numerically.
Yeah.
And if it not, I mark it as a blue.
Yeah.
Okay. And I get the scatter points. No analytics, no pendulum values. Now, in this pendulum picture, libration is a flip, since JZ is the velocity. So libration is a flip. Now, there is a boundary between libration and rotation in the analytical picture, and these are the black curves. Now, if the scatter points would, their boundary between the red and blue would not follow the black curve, the model was not good. It does. The model is good. Okay. In this plot, we left the black curves just to show what happened. Okay. We color shaded the regions in this plane where the analytical pendulum can exist and in what regime can it exist. So there is also an analytical prediction that this point cannot be reached. Okay. And then we put the scatter points of numerical and the prediction of the simple pendulum each point on this plane. Okay. So the model works, and it is a simple pendulum. Okay. Another way to show this success of the simple pendulum model is what we call flip maps. So every plot that you see here is in the x-axis, you have the initial inclination of the inner orbit, which is connected to JZ, and the orientation of the orbit of omega. And different plots are different CK0 values. Now, a flip is a zero crossing of JZ. In the previous pendulum, it was just JZ was the velocity, so libration and rotation was just JZ equals 0. Now it's not, but zero crossing of JZ is asking if JZ max times JZ mean is negative or not. And JZ max and JZ mean can be solved analytically from the simple pendulum. So we can mark the boundary between the regions with the analytical model. Now, we do numerically double average equations of this corrected potential at the different initial conditions, different CK0 and different I's and different omegas, and we plot with blue if there was a flip, with red, with blue if there wasn't, with red if there was, and with black lines, we put the analytical prediction. Where is the boundary between the question, did JZ max times JZ mean is negative or not? Now you can see, moving from different CKs, CK0 changes the topology of the map completely. Some islands emerge, sometimes they go away, and between 0.3 to 0.4, the shape of the lines change, and the simple pendulum model predicts these boundaries quite successfully.
All right, so each point there is just one integration. Are there initial conditions that you can.
Yeah, so in this point, there's no need to scan.
Okay.
So each plot determines CK0 for all the panel. Okay? Above you see CK0 is 0.01. All the points is CK0 0.01. A point has I and omega. That's it. And then you integrate the double average corrected the potential, and you mark with the blue if JZ cross zero, and with the red, with blue if not, with red if yes. And you get these snaps. And then you put on these snaps the analytical prediction of the boundary of JZ maps that JZ mean is negative or not. Okay? And we are talking about positive CK, so this is like a scan of all CK values. I do have time for some time for the third problem. So we talked about two problems: the double average equations plus octupole and the corrected double average equations when the perturber is massive. Now we are going to talk about a totally different, or I think a totally different dynamical problem of a very hierarchical four-body system. So as the setting is quite similar to the three-body, but the perturber now is not one mass; it's two masses. It has angular momentum by itself, although the perturber could have spin, but it has non-negligible angular momentum by itself, which can exchange with the outer orbit angular momentum. So the dynamics turn out to be different. So this is a setting. We have a very hierarchical 2+2 system. And in this system, turns out that we don't need the octupole to let JZ change. So as I said, now we gave angular momentum to the perturber, so it can exchange angular momentum with the outer orbit, and there is a torque exerted by its movement around the inner orbit. And this torque in the z direction changes JZ even at quadrupole order. So this also answers the questions. In this setting, you don't have to wait long for the octupole to work, because already at quadrupole order, solving these initial conditions lets JZ change.
So what hierarchies are we assuming in this case? So there's no, so the only small m is M2 still.
Yeah, the M2
and
is a test particle.
therefore have to be both big for the effect to be. And
although people do simulations with M3 also test particle.
and how about the separation between M3 and M4? Even if it's very small, then you still.
So you need a hierarchical 2+2 setting. This also works for 3+1, but it's like a different subject. For this 2+2, so you have the outer separation. It has to be larger than the two inner separations. And M3 and M4 must have non-negligible masses in order.
So regardless of how close M3 and M4, you can still get.
No. If you take M3 and M4 to be very close, it's not a four-body system.
Well,
You need to give angular momentum to the 3-4 orbit. Okay?
So if you make it smaller and smaller, the separation, then what happens? Is it that the time scale of the
this will become three-body
J's
problem.
evolution becomes longer and longer?
It becomes a three-body problem.
Yeah, okay, but how does the limit
It's not a small separation. It
work?
must take very, very long to do it.
Yeah.
So it's just the time scale becomes smaller.
Yes, the time scale.
Makes sense.
Okay. So these are the same initial conditions as before, but as the massive perturber before, but now M3 is not one solar mass. It actually is composed by two masses. Their sums one solar mass, and JZ changes even at quadrupole order. But waiting even longer, its dynamics is periodic, which gives us hope to solve this problem analytically. And indeed, in some subspace of initial conditions, we can do that. And guess what? Using what analytical model can we do that with? A simple pendulum model. So basically, numerically, we can see JZ oscillates, so it can change just by this dynamics. And the oscillations have some period, they are periodic, so we have some hope. Going back to this plots of CK0 and measuring how much can JZ change in this setting. Now we look at all CK0 values. We plot on this plot with black crosses the measurements from the numerical simulations. So we do the double average equations of the quadrupole. Now we don't need octupole. The quadrupole approximation of the perturber, and we measure how much JZ changes as we move CK0. We start with JZ equals 0. Omega is just randomly chosen, so you have a scatter. And you get this nice black scatters plot. Added above this plot are two values of CK0, where the frequency of Kozai at this CK0 is close to the frequency of the perturbing potential. So analytically, we know the frequency of Kozai in the left panel as a function of CK0. The perturbance has some frequency from its parameters, and there are values of CK where these two frequencies are very close. And it turns out, at these values, we have this striking high increase in JZ starting from 0. So these are the interesting regimes. This is like what we would call a resonance effect between, we have two frequencies, and if they are close, there is resonance. And we can follow.
What is the perturbing frequency?
So what the perturber actually does in this subspace of initial conditions is a precession of the outer orbit. Okay? So as we said, we gave angular momentum to this 3-4 binary, so it can do something to the outer orbit, to the outer angular momentum, stop taking the orbit, right? In the 3-body test particle case, it was just constant. J outer was J dot, it was constant. What this 4-body setting does is allow the outer angular momentum to precess. Okay? It precesses at some frequency, this is the frequency, and this is the frequency of the perturbance. Okay? And when it's at values when it's close to the frequency of Kozai, you get this resonance. So the black crosses are just numerical, but it turns out that these striking features occur at initial conditions where the frequencies coincide. Okay. We can define a new variable, which is the difference between the frequencies. It's not constant because as the driving force moves the orbit, the frequency of course changes, so it's not constant, and we can follow the dynamics of the velocity of this variable. So we have this variable phi, which is phi dot is just the difference. Phi dot is delta, it's the difference between the frequencies, and if we follow the time evolution of delta, we get, using what we analytically know from pure Kozai at Jz equals 0, again, the equation of delta dot is some constant times this sine phi, which is again a simple pendulum. So we can analytically know the evolution of the difference of frequencies and this delta. There is a connection between delta and Jz, which I won't get into, but knowing delta min and delta max for the simple pendulum allows us to know Jz min and Jz max. And basically we know Jz of time. And here we have a comparison between Jz of time from the simple pendulum equations and the double average equations numerical simulations, which we can see that it reconstructs. And now we put red circles on the black scatter of points, and we reconstruct the location and the amplitude of the effect. So this effect is also a simple pendulum model. So we've gone through 3 different few body dynamical systems in the hierarchical setting, test particle approximation, and high eccentricity regime. And we have shown that all 3 can be approximated in the long term. We're using simple pendulum models. I will just finish with saying what I've explained in the dynamics meeting, that basically the quadrupole Kozai-Lidov, what we started with is actually exactly simple pendulum. This is like a different subject. This is not approximated. This is exactly a simple pendulum. This was in the meeting. We've managed to reduce what looks like a complex high E dynamics, multi-parameter initial conditions with like 6-7 parameters, very sensitive to initial conditions, changing the parameters slightly can change the result. They can be reduced in analytical understanding of the simple pendulum model. I think the flip tests of test particle is like analytically solved already. There's a full analytical mapping of flips now. And the way to come is going to 4-body problem, which is a much more rich in initial conditions phase space, trying to track and follow its analytical dynamics. Affiliation. Any questions?
Few minutes for questions.
So going back to this picture at the beginning where you've got these big spikes where you're accessing the high eccentricities when JZ is crossing zero essentially.
Yeah.
That's the condition you want to kind of get maximal eccentricities. There's something there as well perhaps about like the phase of the system crossing this boundary. So I guess you'll either be in a Kozai spike at that point as JZ is crossing. Does there need to be like a special kind of matching up of the initial condition to access the deepest point of that spike? And you see what I mean?
Yeah. So this plot is trying to approximate the full n-body simulation with double averaging approximation of the orbits. Of course, if you in the n-body simulation, there are short-term oscillations of all of these variables, which can get you to some high eccentricity or to another high eccentricity, depending on the phase. Yeah, of course. But in this picture, we are trying to capture the long-term evolution using these double averaging approximations. There are many works that follow these short-term oscillations using single averaging or even full n-body. If you're very close to JZ equals 0, but you're not crossing, these short-term oscillations can let you cross 0. But this is not this work. Yeah. This work wants to capture the very long-term picture, very long-term change of JZ, and to show that follows a simple pendulum model. Yeah. Okay. Thank you.
How high does the eccentricity exactly become here? I mean, it goes very close to 1.
Yeah. So this is like dependent on numerical setting. You can change numerical settings, and it will the exact value of if 1 minus e stand to the -7 or to the -8 is numerically dependent.
But analytically, from the pendulum model, you can predict that.
So when JZ equals 0, this is not pendulum. This is Kozai. When JZ equals 0, your max is 1.
The difference between is just that this happens within an orbital period, so the flip is.
Yeah. So this is connected to Callum's question. But in the double averaging picture, like mathematically, if JZ is constant in the quadrupole order, and if it can cross, and for every JZ and CK, there is analytically known Emax, and this Emax is 1 when JZ.
So for the analytical flip condition that you derived it in the case of low JZ. But then it seems to work up to JZ of order 0.3, 0.4. How high do you trust that condition?
So
like if I extended the vertical axes of this and plot.
So low JZ or not low JZ, why we started with low JZ is we threw terms in the octupole expansion of the Hamiltonian, which are dependent on JZ squared. So basically it's low JZ squared. Okay. So 0.3 squared, this is low. And well, I trust it as I trust it. As you can see, so 0.3 is
I ask a astronomy question. So I of course sympathize with your method of doing things. I think this is beautiful. But the rest of the field is not doing this kind of thing. Mostly they've been just brute force simulating. And these are systems that you can just brute force simulate. And you can do population synthesis very easily and so on.
Yes.
So is there anything new, like astrophysically, merger rates, TD, I don't know, that you think that they've missed that you can capture using this stuff?
Yeah, so I think, or at least in the regimes where we compare the analytical models to numerical simulations, there is no need to save time with the analytical model. So n-body is negligible, and basically in most of these cases you don't even need n-body. And double average equations is like it's no time. So there is no motivation to say, "Whoa, this is very tedious. This cannot be done numerically." We need the analytical prediction to know the result. This is not the case. The motivation is first of all curiosity, but other than curiosity.
Maybe in the four body stuff?
So
that's a very large
double average, yeah. So double average also for four bodies. is like no time. The phase space of initial conditions is much larger,
Yeah,
but
so
the
you can't really
time it
brute
takes.
You can't
time
really
it takes
force
to-
the n body for.
No, n-body no, but for the hierarchical setting, mostly double averaging is very good. So quadrupole double averaging, each initial condition is no time. So you expanded the phase space of initial conditions, no worries. I don't think the point is to know the result per initial condition. The point is that when you see, so you see this structure, okay? You have this divergence, and then you have this zero, and then something, there's like a striking feature. Okay, there is a reason for this feature. Yeah, actually, it's this one. So so you see three regions, is up to the divergence, then going down to zero. There is like an analytical reason for this, for the structure of these functions, fj and f omega, and the zero crossing points. So at points of ck, well, each of these functions cross zero, the phase space changes, and this is the reason there is like a striking shape, the results.
All right, we should leave it there and carry on over lunch. A bunch of us will be going to Rubinstein tonight. So about 6 o'clock. Please. Let's thank Ygal again.